Hello, everyone. This is Suman Vednath, here, the chair of IEEE ET Section PES Joint Chapter. I think we will get started in a minute. I believe our participants are still joining in, so we'll probably give them a minute or two to join in further and then get started. Thank you, everyone. So welcome everyone to this distinguished lecture series, and this is our fifth talk in the series that we have had, and we are happy to host Dr. Wahid Madani for this talk, and I hope there's something that all of us can take away from this talk, and considering that we have had some inputs from our members in this section regarding this talk, and Dr. Wahid has been gracious enough to incorporate some of those interests that have been specified by our members. I'm hoping that you all would have a good session and enjoy the session. So first, I'd like to introduce the topic briefly that we have for today's talk. It's going to be on modern grid and hybrid systems, resilience, sustainability, protection, and operation. I think this topic has been chosen at the apt time when there's a lot of debate going on to define what is resilience, how does it vary from reliability, and how do these terms define themselves, and what do they mean for the system planner, operator, and other interested individuals. So thank you, Dr. Wahid Madani, for showing us some insights and providing information on what do these terms mean. Next, I briefly introduce Dr. Wahid Madani. He is the executive engineer at Gridtology LLC, an international advising corporation and training institution in advanced power systems application, grid modernization, and deployment of emerging technology in generation, transmission, and distribution. Dr. Madani's 40 years of experience spans across system planning, operation, protection, and control engineering. He is an industry leader in developing strategies, roadmaps, and engineering standards for advanced solutions in transmission and distribution systems. A Six Sigma project management trained, Dr. Wahid Madani is recognized for his expert support in grid modernization and deployment of emerging technologies, including wide area systems and RAS, or remedial action schemes. I think we are all excited to hear you, Dr. Wahid Madani, and your great experience can certainly provide us with insights as we look at research into multiple aspects in these areas. Over to you, Dr. Wahid, at this point.
Well, hello, everyone, and thank you both to the local chapter for inviting me, and also to the attendees for investing time with us today, with me today. I'm truly honored.
Dr. Wahid, if I could interject for just briefly a minute, if you may permit me.
Sure.
I'd just like to add one last thing here. I think as we hear this exciting presentation from Dr. Wahid, he has graciously agreed to have, and as a matter of fact, he came up with the idea that we could potentially have an intermediate break-off point at half an hour where some of the Q&A can be taken. So feel free to send us your questions. You can address it to Mustaq in the chat window, or myself, Suman Devnath, or Rafael Wada. Either three of us would be available to take questions from you. And there's Shilpa Marty as well in the call whom you can send messages to. And we'll collect all the questions, and at the halfway mark at 12:30, we will present these questions to Dr. Wahid so that we can get some of the answers to those questions. And we will again have another Q&A session towards the end of the presentation. Thank you, Dr. Wahid, and over to you at this point. And I promise I would not interrupt until 12:30.
Oh, it's perfectly okay, and thank you for interrupting. There's nothing wrong. I'm totally flexible, but I do want to continue recognizing the investment in time you're making. Hopefully, this session would be worthy. Thank you also for the introduction. A little bit of a background I put on the screen regarding my involvement with the industry and particularly IEEE, USDOE, as well as USNSF is on the screen. I have been on 27 operations for decades, worked on system resiliency, system reliability, and I recognize, at least I think I recognize one name amongst the attendees that I can see on my screens. But it's always great to have new friends joining in and making great friends. So with that, I'll proceed. Our topics today is going to be some transformation highlights. What is resiliency? What's reliability? What are the differences? And so on, and challenges that we're addressing. And we're, of course, a little bit, very little on sensors and data tsunami and machine learning. I do have a complete lecture and sometime in the future opportunity maybe on machine learning. So it's not a new topic for power system. There's a lot of strides in that arena, both internationally, I should say globally. So some of uh, the key thing I want to take away is that demand for bundled loss has declined in many parts of the world. And I started to notice it myself somewhere around, let's say 2014, when I actually approached one of my colleagues at that time, a former TVA colleague, Mr. Terry Boston, and I whispered, I said, I don't know if it's me or if it's others see the same thing, but I'm seeing a big decline. And this is 2014, and he told me, no, it's happening everywhere. So that's not my imagination. But you can see there's some projections in California, 75% of the load would be served by clean power suppliers or consumer choice aggregation. And there is one of your questions to me is value of investment, particularly, how does utilities need to make choices in terms of investment, and what is the role of industry to remain relevant, right? And of course, we get into the last topic. I thought you want to be aware. IEEE General Meeting this year is going to be, of course, web-based. But for those of you who are not attending or following the general meeting, that's an internationally attended. It would have been in Canada. But the theme is big data, machine learning, and electric transportation transforming the grid. So to give you a perspective of how timely your questions are, and you're in line with the theme of the meeting. I do have usually a couple of acknowledgements. In this case, the lecture is really reviewing today is much broader than energy and technology transformation initiative. I have a few slides regarding COVID-19. There is a lot of lessons to be learned just from a power system perspective. My colleagues and I are also preparing some additional lectures on impact on education. But that's not the focus of today's presentation. The COVID-19 pandemic has had a lot of new offerings for us to do. The other one is, in this particular case, please keep in mind that some of the energy policy regulations, consumer incentives, and behaviors may be different for many reasons, including system topologies, regulations, and policies. So something may or may not apply to a specific group of people, but nonetheless, because this is an IEEE event, and because this is like more of a broader perspective than just the U.S., please have that in mind as we play. A little bit about energy diversity in the U.S. and electric industry. If you look at this from a perspective of the number of entities that participate in the energy market in the US, majority are publicly owned utilities. There are some government, if you want to call it, entities or federal governments, right? I mentioned TVA, Bonneville Power, for example. There's a number of, but it's very few that are owned by the government. Uh, Here's an example of the decline, right? If you look at this, and there are references throughout, you can see in this case the sightings and the report where they came from, if you would. In this particular case, we can see that there's about a 3% decline on total annual electric sales, okay? And roughly a 7% decline since 2000 on the residential. So this observation that I had, hey, overall the load is, consumption is, and a lot of that at that time, the factor was conservation. Was a lot of, if you remember, at least in California or Northern California, well, in California as a whole, we did have you know, a need for energy, and there was a lot of advertisements about conservations, the benefits of the conservation, as well as, of course, helping with managing. What you see on the lower chart is the manufacturing sector, and more observation is how much of it is generated on site locally. This is more of a one particular, if you want to call it European perspective. You can see that renewable energy sources, roughly, you can see by 2030, the objective is 55%, and as of 2018, they had already got 35%. Coal is completely phased out by 2025. Electricity production, and you can see the amount of the renewable resources and so on and so forth. But it gives you a perspective that it is a global effort. We're making major progress. Are we making globally, are we making, or at least in the US, are we making difference in terms of the CO2? The answer is very positive. We're actually seeing it. You can see here all the way to 2017. The amount of natural gas, the petroleum and the coal and the net coal imports versus the amount of energy, right? So we are retiring equipment. We are retiring resources. You can see the balance, natural gas versus wind, and of course the renewable, I should say, versus what is happening with the coal. At this time, some of the numbers, particularly related to renewables, still include major hydro, but we're starting to actually document and separate natural sources of energy, just like you're seeing with solar and wind. We get into, in this particular case, I thought this may be of interest. We're part of the North American Electric Reliability Corporation. At the same time, we're part of the Federal Energy Regulatory Commission. Our two neighboring countries are part of the NERC. FERC is jurisdiction over the United States. But what's important is in recognition of this, and this is no exception just to North America, but you can see as of March 18th, right, the effects of COVID will be considered an acceptable basis for non-compliance with obtaining and maintaining personnel certification. We do have annual certification requirements for those of you who may not be familiar, 24/7 resources that are operating. Registered entities should notify the regional entities. The effects of COVID-19 will be considered an acceptable reason for case-by-case non-compliance. And then regional entities will postpone on-site audits. And as you may notice, due to a second wave of shutdowns that have recently started, or the impact of the COVID-19, the dates of July are being discussed and possibly to be revisited. This is again one example. In this case, this is from the Terna, which is the Italian power grid operator. It is no different than the one I have for India. There's a lot of different. California ISO is no different. I'm part of the California ISO service area, if you would. So you will see that the dispatchers, that immediately they had to activate a backup system. Most of the regional control centers do have a primary and a backup. So now, how do you manage the resources? How do you manage the shelter in place, if you would, or if they need to be, for some reason, isolated for a number of days, and so on and so forth. This, I thought you may find it interesting. I do have access to certain information from California ISO, so the plots are from raw data and the dates I selected. California ISO service territory is on the left. You can also see a little bit of statistics here. Reason I thought this was interesting is because I had heard that the load pattern, the demand, if you want to call it, for a weekday appears to be similar to last year's weekend. Okay, so one of the things that is really important in the factoring any plots is really California service territory has many microclimates. So weather is a major factor. Where, for example, if you're near the coastal area, okay, you're not looking very often to 3-digit numbers for temperature in terms of Fahrenheit. So I had to look at a fair amount of data to make sure that the weather patterns are relatively comparable before I can put a. So selecting the dates, but you can see the patterns. It's nothing information other than interest. That yes, indeed, it is very clear that a load on a weekday, right? And it's because, of course, consumer behaviors or offices are closed, or those who are working from home, their work patterns, commute hours have been reduced, and so on and so forth. A little bit about electricity demand. Again, in this case, this has to do with Italy, but you can see that the beginning of March, the lockdown occurred, and with partial opening in early May. This is the number, the weekday, or the week in the year. So this is week 7, and so on. But what is interesting is that week 17, well, you will see there's a big roughly 24% drop on week 15 here. This pattern is primarily because it corresponded to Easter holiday, as well as some local holidays. So it's not, if you're in case you're wondering what happened here, that's the explanation. But what is interesting is you can see during the in this particular case, the April 6th through 12th, they had a 24% decline. Okay, and one factor is, in this case, pump storage is included with the renewable resource. And I thought you will find this resource information also useful. In 2013, we had a PPD, or Presidential Policy Directive, regarding critical infrastructure sector and resiliency. And the energy sector is composed of three interrelated segments: energy, let's call it oil and natural gas, and resiliency is the ability to prepare for and adapt to changing conditions, withstand and recover rapidly from disruption. Resiliency includes ability to recover from deliberate attacks, accidents, or naturally occurring threats or incidents, right? So it's an emergent property of a system. It does have risk analysis and the key thing is model. Can these be modeled? You've been hearing, many of you may have been hearing the word model during even the pandemic. So the key thing is, with resiliency, you may not always have historical data. Okay? That's the difference, whereas in the reliability case, there is usually predictable phenomena for contingencies, as we call it. There's a great amount of resource or information also available through the National Academy, and this was commissioned in 2017 to be prepared on behalf of the Presidential Policy Directive. Use of GPS for timing and navigation in critical infrastructure. You look, these are, and this is from the DHS, Department of Homeland Security. These, let's call it the critical resources, are all deemed essential. If you look very carefully, you will see that out of the 16 infrastructures, okay, 15 use GPS for timing, okay, and 13 of them, which are the ones that are underlined, are considered essential. So the use of GPS is, in most instances, considered essential, and it's no longer a desired. This is also from the Homeland Security Advanced Research Project. So GPS operational needs. In this case, their focus is civil GPS, now plays a critical role in modern telecommunication, banking, and finance transactions, and electric power grid operation. Right? And majority of the nation's 16 critical infrastructure would be impacted by an extended GPS signal timing loss. There's a lot of details. Again, it's summarizing this particular case. So, for example, there are recognitions for use of rubidium, the type of rubidium is used as a backup tie into the timing device, and so on. But impacts vary based on the threat level. And there's a listing of the impact items. The list naturally is for power system is beyond this, but this is just a summary. And the timing requirements through the grid vary. GPS primary reference area synchronization is 1 microsecond or less. Through IEEE 1588, as you know, we can get much better resolution timing than 1 microsecond. And a few, if any, timing backups with more than a few hours of holdover. So again, this, from an extended perspective, it's being highlighted and recognized by the Homeland Security. what's reliability from NERC? And again, NERC, North American Electric Reliability Corporation. A reliable bulk power system is able to meet the needs and end use of customers even when unexpected equipment failures occur. Adequacy, having sufficient resources to provide continuous supply. And then security, NERC and the bulk power industry have defined system security. For decades, we have been using the word security from a security assessment. For those of you who have planning background, and over the more recent years, the word security has been extended to include cyber attacks. Again, there's a reference here for you to take a look at. This is just illustrative purposes of reliability versus resiliency. The graph to the left captures the idea of what is resiliency, right? From a magnitude of disruption or improve the speed of recovery to mitigate the effect of an event on the system. The curve that's on the right is a demonstration of reliability versus resiliency. Reliability is driven by trying to understand how to keep the integrity of the system. We talked a little bit about unavailability of data, maybe for resilience perspective. And resiliency is mainly the tail end of the diagram to the right. And it's about understanding the nature of the risk and how this risk would impact the system and improve to recover, right? The challenge with resiliency is lack of data. We talked about that. With reliability, most often we have the data and we can study the contingencies. It's also apparent that there's only so much you can do with the risk. And it may not be possible to, or particularly for a large machine such as the power system, to eliminate the risk. But we can assess it, we can, in some cases, model it, and so on and so forth. So we get into the electric grid, which is a high-value target. Most of our assets on the grid are accessible. And of course, adversaries have a capacity to do damage. From a reliability perspective, you can see, and I won't read the slide both in the interest of time and also the fact that you can read it much better than I can. Reliability and then resiliency, as I have summarized them here. We have two categories reflected on this diagram. We have some natural hazards, seismic, the geomagnetic disturbance, and you will see here man-made or adversarial hazards. And we will cover EMP shortly, as well as a little bit on GMD. But the key thing is, and I've mentioned this to some of my colleagues in the past, from a power system protection and control, if you think about it, the electromechanical relays did not have an issue with cybersecurity. Also, there was no issues with EMP. And EMP is a phenomenon most often really appearing with most recent generation of microprocessor-based technologies and power electronics. So it's just to give you a couple of perspectives. Again, this is a resiliency framework. You can see on this side, we have readiness, response, and recovery. So in this particular case, it's resiliency framework adopted by the National Infrastructure Advisory Council, also part of the Homeland Security, prior to the event, during the event, and after the event. So you're starting to see the resiliency, at least from a perspective of these three categories: under recovery, replace failed assets; restore full capacity, and of course, review learning and adopt future plans. From a system risk, consequences vary, of course, by load served, by the system, by the interconnected systems, and so on. Probability of consequences is a function of vulnerability. The vulnerability varies based on design standards in place at the time, geography and economic factors, of course, asset, visible, unattended, and so on. But the key thing is, from a takeaway from this plot, is the common area where system susceptibility, the threat accessibility, and the threat capability come together. This would be a successful attack. Impact and frequency, of course, lower impact and higher frequency, like thunderstorms. And then we get into high impact, low frequency, like extreme solar storms. Resiliency versus reliability. So resiliency encompasses hazards and events, including high impact, low probability, quantifies the state in which system ends up, as well as the transition times. Resiliency aims to capture both the effects of consumer effects, the grid operators, and so on. From a system planning and strategy, you have reliability. Again, you will look at contingencies such as N or N-1, -1. And I don't know the composition of our attendees, but the N-1 means when you take something out of sequence or out of operation. N-1 is something has been taken out and something else is being taken out. N-2 is a simultaneous. Lose two components at the same time. But given all of these bullets, this is really the point. From a distribution system, it's more resilient effective to make the system smarter and more responsive to extreme disasters than making the system more redundant in terms of energy flow and energy level components. And this slide that you see is a summary that I've put together based on an IEEE technical report. So this is an IEEE definition that's very similar, and that's where the other definitions that I showed you come from. It's an electromagnetic threat, geomagnetic disturbances, solar storm, space weather driven, impacts magnetic field Earth, drive quasi-DC. So these are very low level AC currents. Low level, I don't mean magnitude, this is frequency. So instead of being 60 hertz, they may be in the range of 10 hertz, if you would. So that's why they show up more of a DC characteristic. And they may damage transformers and assets because of the fact that they can saturate the magnetic core of equipment. We may actually have an expert from the substation amongst our our attendees today. So please do speak up if you see some room for improvement. The EMP is again low frequency event, high impact, low frequency, right? And EMP can damage assets for protection and communication, and threats greatly concern some utility stakeholders. Historic GMD events, the most cited event is the March 6th of 1989. It did affect, as you can see, because this is public information, I can cite the utilities. As well as the amount of damage that was reported. Typical event in the 21st century, again, from mid-October to November, a series of geomagnetic storms called Halloween solar storm affected the satellite-based system. You can see NERC considers GMD a high impact, low frequency. And again, there is a NERC PPL, particularly from a perspective of a planning aspect, okay, transmission planning. There are three bullets in there, which is really then another thing is the FERC Order 830, which is the reliability standard for transmission system plant performance for magnetic disturbance. Real quick, I'll show you that within NERC we do have a process which is a phased process approach, and we have system resiliency on this on the vertical axis and continuous monitoring on the horizontal axis, and basically, again, you can read the four phases of the process or stages. A couple of bullets here. The sun undergoes an 11-year cycle where the polarities of its north and south polarities reverse. Okay, probability of a solar storm occurs is greater during the peak of the solar cycle. Hemp, you heard a little bit earlier, and I mentioned, I'll touch about it, but basically it's a short burst of electromagnetic energy, and depending on its source, it could occur as a radiated electric or magnetic field. And typically, the higher the altitude, the more EMP damaging to electrical and electronic components. So as you move towards power electronics, you really want to be aware of some of these. What is interesting is you can actually see in this case the characteristics of the first burst. Okay? So when we talk about GMD, you can see the geomagnetic disturbance phenomena. Okay, and really the difference is the amount of time, the occurrence of time. Okay, so just to give you a perspective of okay, this is the module. I am not sure if you have any questions. I'll be quiet for maybe 30 seconds, maybe too long. You guys let me know.
Are there any questions? I think no, so maybe we can follow.
Okay, we'll proceed.
Hi, Wahid. Sorry, I think I was talking and I didn't realize that I was muted. Apologies for that.
No.
I almost said it. Okay, go ahead.
It's a very common thing nowadays. I think with the web-based thing that we all miss out. It's like you're muted and you don't even realize. All right. So thank you, Wahid. I think it's been an interesting discussion up to this point where we have clearly tried to define what is resilience and what is reliability and how we differentiate between the two terms. I think the insights have been very, very, very interesting for us. With that said, at this point, did we receive any questions or Rafael, Shilpa, or Mustaq in the chat window?
I don't get the questions.
All right.
Covered the material pretty well. Thank you.
Mustaq, are there any questions? He's probably muted. Mustaq, you're muted.
You're submitting through the chat line, so unless the chat line is muted.
And Shilpa, are there any questions again? Okay. There's one thing I think I had as a question. So I did see that there's a definition of resilience that you had from presidential order, and you defined reliability from NERC, from the NERC definition. Just by a close look at it, it appeared like there are certain overlaps between the two definitions. So for example, in the NERC definition, I think you had security to be one of the capabilities that is inherently identified within resilience and reliability rather. And I think you had adaptive capabilities as well in the definition, right? Do these features not get introduced in planning, which means that the term planning seems to have been mentioned in resilience. So Is there some form of an overlap between the two terms? And do you see, I mean, specifically to the definitions that have been provided by the presidential order and from NERC's definition? And do you have any insights in the fact that the risk factor doesn't seem to have been placed within the presidential order? So is that something else that has been considered thereafter, or do you have any further insights on it?
Well, from a presidential directive, naturally that is a very broad directive. So the definition that I would follow, the definition that the system planners, actually I did mention when I was presenting a particular slide, when I mentioned that this has been truthfully definition. That has been created by system planners. This slide comes out of a technical report that's been defined by system planners. So from a perspective of overlaps and possible confusion, I really don't have any feel that to tell you that the potential for someone making a mistake, but from a system planning perspective, I know that the system planners within gridology, we actually have a couple of system planners that were part of developing this standard. Okay. So this is the definition I know planners are following.
Thank you, Wahid. I think that's an interesting perspective. So quick follow-up on that. So you mentioned that that's the definition from planning perspective, right? So now from a planning perspective, is that standardized, or is that something that few of the utilities have defined it at this point?
No. This is a technical report. I can tell you the technical report number too. I don't remember it,
yeah.
The number, but no, this is an official technical report
okay.
published. Yeah, I don't.
Okay.
It's not. I know it's not 68. I think it's 72. But I'll get you the technical report.
Sounds good. Sounds good.
I'll actually put that in the technical report on the slide for that purpose. No, it's an IEEE published report. It came out in 2017. I know that. Okay.
All right. Sounds. Any other questions before we move forward? Okay, Wahid, over to you.
Okay. All right. We usually start every session to make sure everybody is fully attentive with a quiz. So if I was to ask you what are the 4 R's in the modern grid, I'm hoping that you have a pretty good idea of what they are. Since this is not a live session, I presume we can give you the answers, right? Now, I usually start with a little slightly perspective of when you go home. Of course, we're all working in a different environment today, but if you ask your family, tell you what are the 3 or 4 R's in the modern grid, I don't think you're going to hear any of these. Okay, so we got to be careful from a perspective of us being engineers. Of course, we have a feel for reliability from a family or a meaning public. It is expected. The point I'm trying to make is, of course, I expect when I turn the switch on, the power will come on. So therefore, it's not from a public perspective. It's given. It's expected. Okay. Energy continues to evolve. We're by now pretty familiar with traditional energy systems and markets, where we had a utility, if you want to call it, or one of those entities that was in charge of producing energy, and then it was distributed, and we had consumers. On the right, we're seeing the evolving market, from distributed resources to electric vehicles to storage, to smart grid, right? So the energy landscape has transformed and continues to transform more rapidly in the next 10 years than in the previous 100. And again, when we talk about value proposition, the investment, you want to be cognizant of this, and somehow the utilities have to transform their operations, right? Improve network efficiencies and so on. Next generation of renewable sources. Again, this is got a reference, so you can feel free to take a look. Roughly 37% wind and 39% hydroelectric. We have a portion of the solar as well. U.S. utility annual battery installation. Thought you may like to see this because this typically comes up. Where are we on the batteries? What's the technology? And just a few minutes ago, I referenced to a FERC order, and I'll cover that in a minute. See how real-time information you're receiving. But if you look at the data was not fully accumulated for 2018, so that's why it's not in a complete dark. So, but you can see that there's a pretty good significant, and of course, immediate question is what's the cause of these drops? The cause of these drops is based on the report. It seems to be the investment question because of a number of deficiencies identified, as well as technologies that were being introduced in terms of batteries. So the utility scale, if you want to call it, drop, because you'll see that, for example, one is a fire inside the batteries, right? We all have heard about the technology in the cell phones, the lithium-ion batteries, and so on. So that's part of this major drop, because utility scale or utility investment is a life cycle. It is where it's not similar to our handheld devices that once every 2, maybe 5 years, give or take, you replace it and get a new one. Okay? This is not an individual investment decision. This is a ratepayer, whether it's FERC or the local, state, and so on and so forth. I thought you like this, the battery storage systems, the market outlook, and risk. Just 2 days ago, on July 10th, yes, 4 days ago, which was Friday, I think, July 10th, Federal Appeals Court of District of Columbia upheld the FERC Order 840. It's a very significant announcement, and again, there's a reference for that for you. It allows the transmission operators in the U.S. to open their markets for energy storage. So that's another reason for a slow response. Okay, the states wanted to have a jurisdiction over specific, again, control of the utilities. And I don't know how much you're familiar with what's the difference, whether it's a FERC or whether it's a state level. The difference is when a utility transmission operator has to put together their budget, who approves it? If it's a local state, oftentimes those rates are also scrutinized beyond just the FERC level. They're scrutinized by what we call the Division of Ratepayer Advocate. Okay, so this slows the process down and so forth. But ruling includes FERC having jurisdiction over how energy storage interacts with interstate transmission market, okay, even if these systems are interconnected under the regulation of the state. Another piece of information I thought you'll find useful is the Newton-Evan research. Again, this is fresh. This is June of 2020. You can see a reference, the publication, The Storage Revolution on T&D Work.
Can you watch?
I'm sorry? Okay. the U.S. energy storage market will grow more than 5 billion by 2024. Now, as a result of this ruling, some of this may actually get approved. Lithium-ion batteries are the leading technology for utility as well as commercial and industrial. They're used in electric vehicles and other consumer electronics, so it results in a decline in cost. Risk is fire. And there are a series of items here, and these, if you look very carefully, the years, they correspond very closely to this chart. Okay. Getting to what's called behind the meter, I just need to let you know this terminology. That this has to do with solar rooftop installation, let's say residential or some small commercial, where they're directly using their own energy source through the, let's say, solar rooftop, right? So the Northern and Central California service territory, the second largest growth in U.S. chemical energy storage in 2015, okay, was a non-residential behind the meter, okay? And almost 5 megawatts was the biggest quarter, and over 300 jump over the first quarter of 2015. So in Northern California service territory, until about a year ago, I don't know about the impact of the recent COVID-19 and so on, but we used to average 6,000 applications per month for rooftop installation. So you can see over a period of maybe 8 years, that translates to quite a bit of loss of revenue, if nothing else. Energy landscape. When you look at this, I want to make sure that it's clear for you that these entities are not consumers. Every one of these entities is a producer of energy. Okay, and they all have to come into the grid. One of your questions was investment and where do the utilities need to invest. This amount of energy will naturally translate to, does the grid, the transmission grid, have the capability to transport? Right, particularly as the cost keeps going down. Even, I don't know if you noticed during some of the earlier slides of Europe as well as in India and the US, the import was increased quite a bit because of the value of energy. So the amount of consumption is a direct related to the lowest amount of the lowest cost energy, and so therefore transmission needs to be reinforced. Maybe that's but the key thing is, what are we going to do with all these generators? Here is the California ISO perspective for 2030. We have a surplus. Now what are we going to do? Renewable portfolio standards is showing that this generation mix is excessive. About 2 years ago, you may have heard that California ISO was expanding its control area to, say, Arizona, as well as possibly a little bit of Utah, but a couple other states. And the question was, what's the driver? The driver is, for now, we have a solution how to handle this overgeneration, because the demand was in other states. So we can now transport the amount. But at some point, this happening in every state, I'm not sure what the next solution is. But for now, we can supply low-cost energy during peak, if you want to call it, or the renewable energy. For now, we have a workaround Not sure how PJM, for example, or Midwest ISO are tackling this, or have they come to this phenomena yet, or do they observe this? So what has happened is we've changed the control shift. That's what we're discussing. On the left, you can see we had the distribution system, where we had, if you remember, we talked a little bit about the source versus load. So most of the responsibility for resources were at the utility level on the left, you can see, and then of course it was transported and consumed. On the right, you can see we talk about 50-50, right? So this is what you're looking at. So now the distributed energy resources must act as a system resource, okay, storage, curtailment, and so on and so forth, right? And of course, the figure shows what we're seeing, what we're observing as far as changes in the dynamics. This is a slide I've used, created this before, so you may have heard me talk about it a little bit. On the left, you will see what is now we refer to it as the past. So if you consider me as a past, this is all I had to deal with: safe, reliable, and affordable. Okay, we went through a transition, and now the future. Look at this. I am very happy that we have a huge team of very energetic youth resources that are going to handle all this. The safe, the secure, the time frequency synchronized, the reliable, the affordable, the environmentally responsible. But you can see what happened from the left to the right. So for those of you who are starting your career in the utility, I congratulate you. But please keep the lights on my behalf. How's that? So this is what has happened, right? On the left, again, this possibly maybe prior to the COVID-19 shelter-in-place requirements. On the left, you will see a highway where it's one lane on either side. And sometimes actually we want to go on those highways because it's isolated. Then at some point we transition to the freeway. And of course, we have now transformed to a seamless access of highways. If you think this is just alone, again, this would be the air traffic controller environment, which is somewhat similar. You can see we're in a predicament now. Every one of these dots is a flight. Of course, I wanted to acknowledge that the impact includes or excludes impact due to the ongoing pandemic and the shelter in place. Of course, air traffic controllers may have a lot less flights to deal with today. The roads may not be as crowded. From a market for a grid in transition, of course, you have to have the resource flexibility and the grid resiliency. What you're seeing is, of course, quality of being easily without breaking or bending without breaking, flexibility through products, pricing, and settlement. From a grid resiliency, the capability to recover from difficulties, and of course, focusing on ways that the market can incentivize, if you would, investments that can support grid resiliency. This is on distribution. Since most of the focus is on transmission, I just thought at least I'll acknowledge things that are happening. Distribution management systems and the DSOs, distribution system operators. In real time, you're going to see hear things more and more on estimation. Then you have analysis, which is again the power flow and short circuit analysis. Some of this I may actually been covered by some of your previous DLPs. I heard this is your 5th session. So what you're seeing on the far lower left, that diagram, is what's actually being experimented. It's now in its 4th year in the Nice, France. We do have a small community, if you want to call it, of 500, give or take, uh, smart systems that they can bid into the market. So there is a distribution operator. Much like the California ISO, you would have a distribution system, and there's possibility for others to come in, but the consumer or the energy supplier can get into the market the night before, and they have time, maybe a couple hours before bid, to change their mind. So that's how much flexibility is being supported. What is happening with all the characteristics, right? We've changed the load composition, right? You know, when you walk into any energy environment conscious business as well as residential, you will see that all the lights, incandescent lights, have been replaced. So we have electric vehicle charging, various straight drive motors, right? So distributed energy resources are coming along, right? Then we have the changing dispatcher mix, higher penetration of renewables, variable resources. Then we have this intermittency issue. Are they available when they're called for? Then again, you'll see some things like ramping needs increase for the load, right? Retirement of large fossil fuel generation plants, changing system inertia. You're going to hear these words with other slides as well. But on the other hand, you have the risk, right? Changing resource mix, right? Potential for lower inertia with retirement of coal or oil fired. The key thing is the system is in transition. That's if we were building from, let's call it a greenfield system, we would have had a system that would not be, at least some of these things may not have been as much of a concern. You have the generators. You want to remember that this renewable resources in the past, say, maybe 10 years, 10, 12 years, they have gotten a lot of ground. But you have a lot of generators that have actually received approval for operation. And again, these are life cycles. So they may have a 30-year commitment to generate, and they happen to be on their 10th or 11th or 12th year. We can't shut them down. Okay, first of all, the investor hasn't gotten their money back, right? Investment. Second thing, so you want to be fully aware of the operational challenges, just because why can't we transition? So if it was a greenfield, it would be different than if you are in a mode. It may take some time for a system to be completely replaced with renewables. And what you're seeing is what are the challenges to get there. Interrelated technical areas, right? DERs, including the photovoltaics, are key drivers for transformation of electric grid. Grid performance and reliability, maintain and enhance efficiency and reliability in the cost-effective, safe manner, right? With hundreds of gigawatts of DERs deployed on the grid. Dispatchability, ensure DERs are available on demand. Address intermittency. Power electronics, develop inverters, converters, and other devices that maximize the power output while ensuring overall system performance, safety. The other challenges on the distribution system planning and operators are fundamentally different than transmission. Bidirectional power flow that affects protection and control. The present distribution system's primary voltage control equipment are voltage regulators, load cap changers. Okay? How do we integrate the new technologies, if you would, in power generation sources? And you can put the bidirectional flow. Integration of distributed PVs may cause excessive operations of these assets compared to baseline operation without the PV. I thought this would be of interest to you. I'll try to be quick on these. in the interest of time and Q&A. But basically, this is an event that occurred in 2016. The key thing from this is, of course, there was a significant import. You can see that there was a severe storm, a number of wind farms separated at bus 508, and I have tried to circle them to make it quick reference so you can see it. And then eventually the South Australian grid separated from the rest of the system. And of course, some statistics on the impact. But wind and PV was at 50% of the total demand. Conventional was 18%. Okay, and this is where the really main issue is. And imports were at 32%. Imports are down here, okay, from Victoria. The following the black start in restoration, of course, they increased contingency reserves. Okay, in other words, they made sure they limit the flow. They added margins to interconnect, which are down here. But again, the real takeaway is, what's the balance? How did I balance the system? Nobody was anticipating this severe storm, that's granted, but at the end of the day, there's the impact. Okay? And the reaction from this is, by the way, made possible by a report from the Australian Energy Market Operator, AEMO. I think if you type that in, you can probably get to this report. But the proliferation of the renewable energy took a negative observation, that if we didn't have that much renewable, okay, we wouldn't have this issue. And that's really a negative takeaway, but I thought that as opposed to, hey, we shouldn't have had operated for this. Real quick, just to show you, again, you can see imports down here on this diagram. I just thought that for those of you who are a little bit more on the analytics side from a system planning perspective, the rate of change of frequency, it's really important. It was 3 times higher than test reports of the manufacturers of generators. Okay, and you see, and 2 out of 3 TIPS units, 502, if I captured it correctly, it's 502. On the upper left-hand side, disconnected due to unload lockout conditions. But so just be aware of it. Under frequency did work, but apparently the system, as you can see, the system recovered. So under frequency reset, another disturbance right behind it, and under frequency had not completely reset, so therefore it couldn't restart. This is another challenge for those of you who are in the protection and control world. Inverter response to system to short circuit. The left side is what all those protective relays are designed for. You can see that there is sort of, if I can use the word, ramp down. Normal condition, no problem. So if you're connecting something to the system and everything is, as I refer to it, rosy, as everything is operationally correct, it's not an issue. The issue is when a system has a problem. There's a number of things right through. You have heard voltage right through. Now there is a frequency right through requirement through that IEEE 1547 and so on. A little bit about what's coming up. Examples of what we call hybrid power plants. In this particular case, you can see a solar PV and the battery bank. Okay, we have the solar arrays and the battery banks. This is a collaboration work with several universities as well as the Department of Energy. We're working on addressing all this, the bullets that you see underneath, right? The PV inverter dynamic state. For example, let's say something that's easily understood for our general colleagues, battery. These batteries are not always fully charged and they're not always fully discharged. So the state of battery charge is also a factor. Manufacturers of these technologies do provide monitoring. But again, this is not about just the level of, it's about how it integrates with the power system. And I won't take, this is another example. In this case, you can see a solar PV and a gas turbine. I have put the word grid forming. We have two terms. One is grid following. That means, let's say, if this was a 1 megawatt, let's say, or 5 megawatt solar array, okay, connected to a 60 kV or 150 kV system, it really may not have the amount of source to be a grid forming. It is following the grid pattern. In this case, because it's a gas turbine, it may be, let's say, 100 megawatts. It can be a grid forming system. So if you have a solar and a generation, so that's why you're seeing, in other words, it can serve a load of beyond the one or 2 megawatts. It can connect to the grid. And in this case, you're seeing hybrid power plant. In other words, there's one plant here. On the left, there may be other plants. And how do they? A couple of slides on system integrity, and we're transitioning to wide areas. In this case, system integrity protection scheme. It may be a local distribution or a transmission, or maybe a system-wide. And I thought you will find this. This is a 2009 report, a 2010 transaction paper. So if you have IEEE members, you should be able to access these. These are the types of different schemes on the left. And I won't take the time to read them, but just so you're familiar. Participation from the industry worldwide, you can see the number of participants in this survey. And there was a 2007 report as well, and this one had somewhat similar, it was not as broad of a coverage of all the schemes. The other takeaway from this roughly 900 or roughly 1,000 entries for the question that we asked, and there was a dictionary, if you would, specifically to make sure that all attendees respond to the same question the same way, or at least to the extent that's possible. So we made sure, for example, under frequency load shedding is not part of this survey. We knew every utility everywhere in the world they have under frequency load shedding. So this 950, if it includes under frequency schemes, it's only those that are communication based. They're specifically a system integrity intended. In one case, I can tell you Tokyo, for example, did have one scheme where they were monitoring frequency from 3 different parts of their system, and so supplying the system, the grid that was bringing energy to downtown. What is interesting from this is 51% of the schemes are now identified as system security. Okay. The original intent of these schemes at one point used to be system security. Roughly 50% are now being used for normal day-to-day system operation. This is not one country, this is not one utility, this is global. That's what it was, IEEE's report on global industry space. A little bit on oscillation, power area oscillations, or groups of inertia between large systems. I thought WCC may be a good quick reference. We identified oscillations between British Columbia and, let's call it the United States, or North America, or Western North America. We do have east-west as well as north-west. The disturbances can cause angular change, and this system can easily get out of control. In other words, depending on, again, reliability and how you do system studies. I thought that this plot may show you a little bit. This is a complement of the Bonneville Power Administration. Malin is actually the borderline between California and Oregon. So this would be right around here would be Malin. And then Devers is in this case here. So it gives you some ideas of the what oscillation is. Now, the reason you want to know that is the next question that you've asked, and that question was, what's the impact of high penetration of inverter-based generation to oscillation? We think that so far, of course, we are still in study mode. We do know that high penetration of the inverter-based generation below 50% will not change the structure of the really a speculation. I've seen studies that show actually even much higher numbers. That as long as you're below 100, let's call it, or 75%. But what to expect at high penetration? Existing structure of oscillations and related continues to exist for some time. Reduced number of local and inter-area modes and change in mode parameters. Of course, with the inverter-based systems, particularly depending on their size and so on, we're trying to figure out the PMUs and the traditional PMUs that were installed at one point in many utilities. There are some exceptions. They were really for serving purpose to ISO. In that case, they were at 30 frames per second. And if they're above 100, if they're above 60, so that means 120 or 240s, and there are some installations, those can participate in identifying oscillations, even for inverter-based. Of course, the other alternative is point-on-wave, where you have very high sampling rates. What's a wide area monitoring system? Very quick again, you can see you have a series of dynamic analysis and post-event factors. You have low carbon energy systems. You have distribution. So these are all the factors that have to go in energy management system. What's a PMU, right? It's the latest precision timestamp measurement technology, right? And it's for higher resolution. So the easiest to really compare it with, it's really, of course, this is the SCADA display. This is a PMU. So it's really a comparison between, let's say, taking an X-ray versus an MRI or a CT scan. So you can see that X-ray as technology has not gone away. It's still being used heavily, but there are times where MRI is needed, right? So in this case, SCADA is 4 to 8 seconds. In the case of the PMUs, you can go up to, at least technologies that are in the market. And in my view, that's just my perspective, is that they really show the DNA of the power system in real time. If you were looking at it a substation perspective and everything was being monitored in the substation, you could also say that digital fault recorder was monitoring the health of the system. The difference here is the data is exchanged, the network that's associated with the interconnected power system. It's not a localized monitoring of the equipment, if you would, or substation particular. Improve security, increase transfer, and system analysis. These are the three main areas. Wrapping up here, again, control room operations, wide area situational awareness, engineering analysis and big data, and of course, transmission operators. So if the investment is for serving the data to another entity, in this case, let's say the ISO, that's a different perspective than if the investment is for the transmission operators. And that's really the key. In terms of machine learning, as I mentioned there at the very beginning, there's tremendous progress on this for power system the past, I would say, decade. But basically, all the data is shown on the left. And of course, we have this tsunami of data. We can leverage that. How do we approach with, particularly, do we need supercomputing technology? So that's basically something to wrap up with. But today, crucial economic, social functions depend on resilient, secure, and reliable operation. Energy-related carbon initiatives and grid modernization are in full gear. Secure and load control at the distribution is becoming a key contributor. A changing environment requires a transformed grid. Right? Immense investment in power system upgrades and deployment of advanced technology. Digital substation business case is becoming evident. Of course, I can tell you that during my era, justifying a digital substation was not as more evident as it is today. And of course, we talked about machine learning. Some of the initiatives, and I thought that's good, interesting for everybody that's participating on this DLP. Machine learning and robotic inspection, cognitive computing, right? Today you talk to your handheld devices, if you would, right? You have a human-machine interface through voice. And then, of course, the most recent topic is machine governance, machine ethics, social robotics. So to wrap up, energy conservation and resource transformation are making positive environmental impact. Consumers have become early adopters. I can give you a number of examples of those. Today, there comes a new technology, for example, on the handheld, and you see people, consumers are standing in line the night before just to get their hands on the first one, right? Distributed energy resource penetration will continue to grow, and that would bring the cost. Managing system impact from DER is a concern for utilities and ISOs. Getting to improve system observability. We talked quite a bit about these, but data mining, machine learning, and then sustainability roadmap and life cycle strategy are key in rapidly evolving grid. And of course, last but not least, operation lessons from the current pandemic environment will offer new thinking in investment, resiliency, and managing the grid. With that, I thank you for your time, and if you have questions, please.
Thank you, Wahid, for this talk, very interesting talk. At this point, I'd like to also thank our fellow partners from the Chattanooga chapter who have also graciously participated in this talk and supported this talk. Wahid, I think it's been a lot of information, and I'm sure that you send us the presentation and we post the recording, a lot of folks will certainly take a look at it and benefit further from the information that you have placed in the presentation. I think at this point we're open to questions, and feel free to send us the questions through the chat window to Mustaq, Rafael, or Shilpa. So Mustaq, Rafael, or Shilpa, do you have any questions?
I have one question. In South Australia blackout study, why did the system separate? What was the trigger for the system to separate?
The separation occurred because there was a series of outages. There was a storm. Severe storm damaged several remote transmission systems. Okay, the main reason was that, well, the studies show, the analysis shows that the convention, there was not sufficient reactive voltage support. Okay, the reactive voltage and inertia would have come from the conventional generator. Okay? And the amount of generation, the amount of traditional synchronous generation in operation was below 20%, as you can see, whereas the PV was dominating the generation. So I don't know if that answers your question, but basically you can see that a sustained action. So all of those generators that were in this area, the wind powers, they dropped off. So I can give you examples, for example, and some of you may or may not be familiar with some of the outages in the Pacific Northwest. The 1994 outage, we had nuclear plants each supporting 750, in excess of 750 megawatts of generation well into the disturbance until the system completely separated. Then under that condition, the generators had to drop off. But in this case, in this instance, the units are not designed to provide reactive support. So the outage occurred, this series of storms, and with that, the units immediately tripped. It's now being addressed, if you're wondering, it's now been reactive support is being addressed as part of that I showed you. Okay, we're talking about identifying, so the technologies are real and reactive power. You can see that on the last bullet. Okay.
Yep.
Hopefully that answers the question. Please communicate now or later. I'm okay with it.
I think that sounds good, Wahid. Let's probably look at other questions that might have come up as well. Rafael, do you have any questions?
Yes, I do have a question, and it is, what could be the potential benefits of introducing hybrid PV systems in distribution grids? Will the distribution grid be assumed to island by itself, and hence the grid forming services provide a value proposition?
Okay. This is slide that's on the screen is actually a real power system that is being, as I mentioned, it's a big initiative that we're working with the Department of Energy. But in this particular example, this is a 1 megawatt system, okay? Meaning as far as, and the feeder is a 60 kV feeder. On this case, it has one consumer tapped off of this feeder on this side, and that is a commercial, large commercial customer. And on this side is the utility, as you can see that. That's a, as I mentioned, 60, maybe 70 kV, give or take. But in terms of, we're now into, we're building some advanced systems, but once we get through this advanced processors and which we can do this, we're in a stage where we're identifying whether or not we can create an island and test the system under that island. It really depends on how much the capacity of this, let's call it a generation source, relative to the system that is supporting. We do not anticipate this example, we do not anticipate this to become a grid forming. We know this will be a grid following system. On the other hand, will be a grid forming system. Because of the size of the units, because like I said, we're looking at roughly about 100 megawatt system. It is an actual installation that is taking place. It's not in service. It's not, it's broken grounds. We're looking at 2023 for this one. And the size of the units, as well as in this case, it's a combustion type generator, and also a solar, which would be about 100 megawatt each. Okay, so this is a pretty large size project. Again, this is under two different. This time, I think it's not two. So these are actual field installations in progress. Does that answer? Well, again, if it not, please follow up on the question. Okay, next.
Yes.
I have one more question. It's from Parul Kushal. Since pandemic is affecting the demand as people are working from home, do you think it has also affected the electric generation in US? So how do they predict the amount of generation to meet the demand?
Wow, it has certainly affected the again, generation has three separate factors, right? We're talking about the conventional generators and, of course, efficiency, energy efficiency factors, and intermittency / availability. What we are seeing is imports have increased tremendously. The low energy cost, the lowest energy cost seems to be, at least in Europe, as well as I can tell you the same thing in India. I have reports from these, as well as in the US. So we have seen many industries that are shut down. So if due to the shutdown, naturally, they keep minimum load on, correct? They're not running at full capacity. Some, as you noticed in some of the earlier slides when I was showing the amount of load, some industries have a base load. That base load requires it. But we are seeing that the load patterns are changing. We are seeing that that I mentioned the transfer or low-cost energy imports are significantly higher. But we're also starting to see, particularly in Europe, as things are starting to reopen, things are starting to go back. Now, again, if we have another shutdown, such as the one in California, of course, then it's sort of swings back and forth. Long term, I do not anticipate. I do anticipate things to go back to normal, but I don't know when that normal is. W Health Organization or World Health Organization yesterday announced that it's not in the foreseeable future. I don't know how many of you heard that, but anyway.
Okay, any other questions?
I have one. This is Shilpa here. So it appears that, so the question is, it appears that there is a generic assumption that the renewables were the problem for a South Australian event, but it doesn't provide any specifics in the report to improve the performance in the existing system. So do you have any insights on the potential solutions for this?
I'm sorry, I it was intermittent. Can you repeat the question, please?
I'm sorry. So the question was, it appears that there is a generic assumption that the renewables were a problem for a South Australian event, but they did not provide any specifics in the report to improve the performance in the existing system. So do you have any insights on the potential solution for this?
Well, it's been a while since I actually looked at the report, which was the Australian Energy Market Operator report. I do know that there is, from the two slides, the immediate, if I can use a high-level takeaway from governmental perspective or political perspective, may have the appearance that the renewables are getting the blame. I don't think it's as much. It's more so that there's two factors. One is understanding how these renewables interact with the grid. Okay. And I mentioned the reactive power supply, if you would. But secondly, in nature, the power electronic systems are designed differently, yet they're at this point interconnected with a hybrid. They're being operated in a system where the load may not necessarily be the same as the design of a power electronic system. I do know that the performance requirements for the renewables, I had a slide, and I don't want to take too much of your time. I did have a slide that said the performance requirements of the let's call it inverter-based, but power electronic system should be no different than the performance of a traditional generator. So I don't remember specifically whether the report on the Australian Energy Market Operator report, to what level they got into conclusions, and one of them being specifically related. I do know that they have acknowledged that the way the system was being operated, it basically could not have supported the contingency that maybe it was unprecedented, maybe it was not anticipated. They lost multiple lines due to a heavy storm. Maybe they should have changed the system, anticipating this storm was coming. I mean, that typically storms are planned. I don't want to plan, but anticipated. So what happens is you would know hours before it happens. Maybe under that condition, they needed to have more reserves. Maybe under that condition, they wanted to have more traditional units on. So it's a combination of really many factors. One, and I think I touched on all of these during the presentation, but maybe a little bit differently. There are unit commitments. At the same time, there are the cost of energy, right? And the third is what we call must-run units. And that's the example I was giving you where I said the unit, when you've just been installed 10 or 12 years ago, you still got at least 18 more years before it's fully recovered in investment. So those are must-run. So maybe they should have sort of balanced these and had more of the traditional units. But I do know that today's manufacturers or today's technology of the inverter-based system is being informed of the system requirements. So the manufacturers are getting more and more informed from the perspective of how, that's why I was referring to write-through, right? Many of you may know about the write-through. Write-through means you should be able to write through the system. So the voltage write-through, I can share with you about 3 years ago, well, not 3, maybe about 6, 7 years ago now, there was a 230 kV fault somewhere within southern part of the state of California, and there was 3 major resource plants that immediately dropped. Okay, immediately. So the systems need to be designed for those write-through, and these generation sources were not in the immediate area where the fault was. Now we are hearing the word frequency write-through, right? With the frequency comes what we call the reactive margin.
Thank you so much. It answers the question. Thanks a lot.
I hope so. Yeah, long answer to a short question.
I think Wahid, we've had a lot of good questions, and there might be more questions that will keep coming up. What we would do is we would collect all the questions and relay them to you separately through an email. Since you've covered a lot of material, I wouldn't be surprised if there are more questions coming our way. And I thank you for patiently taking all the questions and answering all the questions in depth. Thank you, Wahid, once again for providing us with this very intriguing and extremely detailed lecture that you provided us today. And we hope to continue our coordination with you and continue to stay in touch. And we will reach out to you for further processing and any other information that we receive from our chapter members. Thanks once again, and thanks for all our attendees for attending this talk. Feel free to let us know if there are any questions, and I'll relay them to Wahid as we move forward.
Suman, just one more thing to all the participants. If any one of you would like to get a certificate, please email me at rafal.voida@ieee.org, and we will arrange the certificate for you.
Thank you, Rafael. Thank you, Rafael, for bringing that up, actually. And this is for the PDH and CEU credits that folks in our region might be interested in getting.
Yeah. Okay.
If I may just say one more thing, I want to thank all of the attendees, but I also want to credit you again for your questions. So if this was a lengthy presentation, it many of these questions or the topics were generated through you interfacing with Soman and me. So thank you again for asking these questions ahead of time and thinking, helping me prepare for this lecture. So thank you again.
Thank you.
Thank you, Wahid. And everyone, please stay safe, and we look forward to your participation at our next talk. Take care, everyone. Please stay safe.
Thank you.